Hello everyone, today we are going to be starting into Chapter 11. Chapter 11 is dealing with probability. In this section we're going to specifically talk about theoretical and experimental probabilities. These are kind of the basic forms of probability to get us started, and then we'll talk about what's called compound events, or when we start to combine things together, in the next few sections. So, I apologize before we get too far into this. This is going to be a relatively long video. There's just lots of different little things that can happen with probability that we need to make sure we're comfortable with. So the first thing we're going to have to be able to do is we have to be able to figure out how many different things are possible. Okay, and that's a very specific type of question depending on the situation that I give you. So we're going to actually start with an example here. I give you a table here. And in this table, I'm giving you the choice of a yogurt flavor, a fruit topping, and a nut topping for your yogurt parfait. So you're making a yogurt parfait, you get to your choice of these. I know your lines aren't super clear here, so we'll just split this up. So you got two flavors. You got vanilla and plain, which I guess are probably similar, but we're concerned would be different. Fruit, we have 5 of them. And then for nuts, we have 3 of them. Okay, we got almonds, peanuts, and walnuts. So what we need to figure out is, well, how many choices do we really have? So really originally, you have a choice in your flavor. You can either go plain or you can go vanilla. Okay, from there, I get a choice of 5 different options. Okay, those 5 options correspond to our different fruits. Okay, I'm not too concerned about reading those. I just need to know how many options there are. Okay, then for each one of those, I get 3 choices as far as the type of nut that I put on each one. So what I just drew here is what we call a tree diagram, which that term should make sense. It kind of looks like a tree. You got your branches going out. Okay? And what I'm doing is I'm making a different branch for each of those choices. So for example, this first one here, where I have P, well, that's plain. P here is peaches, and then A is almonds. So that's one option that I have. But I could also go down that same route, but choose peanuts at the end or choose walnuts at the end. Those are my different choices. Or I could make a different choice of fruit, and then I go to one of these other ones. Or I could have the vanilla, and I can make my options down here. But again, the question is really, how many of these do we have? Well, if I look here, what I've done is I've split into 2. Then I split into 5, and then I split into 3 on each of these. And I would have the exact same thing down here. So what I'm doing is I'm taking the number of choices that I have, and I'm combining them together in some way. But if I look, this 2 means that I need to count the 5 2 different times, because I could choose all of those based on plain or all of those based on vanilla. I could also do the same thing with the nuts for each of the different toppings. So I need to multiply these together. I'm counting all of those options. So if I do that, 2 times 5 times 3 is going to give me a total of 30 different options. And you can start to see those here. Okay, if you count how many I have in this top half, there's 15. And I would have those same 15 just with vanillas instead of plain. So I have 30 options. So I'm multiplying them. That idea of multiplying the number of options you have at each choice is what we refer to as the fundamental counting principle. So let's go ahead and get this written down. It's a little bit wordy, but we'll talk through it here in a second. So it says, when choosing one item at a time, the total number of combinations can be found. Let's run together. By multiplying the number of options at each choice. Okay, so I'm simply taking the number of options and I'm going to multiply all the way through. So here I had 2 options for flavor, 5 for fruit, and 3 for nuts, so I multiplied those together. Okay, now we're going to do the same thing for a couple different other scenarios as well. Okay, first one, passwords are a very common example that we'll talk about, so we'll have a couple examples with these. Excuse me. Number 2, a password for a website consists of 4 digits followed by 2 letters. The A and Z, letters A and Z are not used, and each digit or letter may be used more than once. Okay, how many unique passwords are possible? So what I'm going to do here is they've told me basically what the password's going to consist of. That I have 4 digits and then 2 letters. So these are, I got a digit, 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 and then a letter, and another letter. Okay, well, let's look at how many options we have at each choice. Digits, we're talking about numbers 0 through 9. So counting the 0, I end up with 10 digits. Okay, and because I'm allowed to use them more than once, I could use those same 10 digits for the second one, the same 10 for the second, or the third, and same 10 for the fourth. As far as letters, there are 26 letters in the alphabet, but they have specifically told me that I am not using the letters A and Z. No idea why, but I have to work with it. So instead of 26, I take those 2 out, and I'm left with 24. Again, because I'm allowed to repeat, we're going to leave it as 24 for the second option as well. Now, what the fundamental counting principle tells me to do is to take all of these and multiply them together. So in my calculator, real quick, I'm going to do 10 times 10 times 10 times 10. So my 4 digits times 24 times 24 for my 2 letters. Hit enter. This is going to be a relatively large number. It's 576,000. So 5,760,000 passwords. Okay. Now I'm going to take that same scenario, but I want to make just a slight change to it. What if we do not allow letters or digits to repeat? So for my first digit, I still have 10 options. That does not change. What's going to change is when I get to the second one, I've already used a digit. I don't know exactly which one I used, but I know I've used one of those numbers. So I only have a choice of 9 left for the next one. Same thing happens when I move to the next digit. I've used now 2 digits, so I only have 8 left that I can use, and then 7 left for the last digit because I'm taking 1 away each time because I've already used that as I go through my password. Same thing's going to happen with the letters. We start with our total number of possible, but because I don't allow that repeat, it's going to go down 1 to a 23. Now, because I've taken some of those possibilities out where it repeats, I'm expecting my number to be a little bit smaller. If we go ahead and multiply these, 7 times 24 times 23, I get about 2 million, almost 3 million, so 2,782,080 passwords. Okay, so probably say roughly half of them are gone now because of those repeats. Let's move on to example 3. You have a make-your-own adventure video game where a player can choose 6 different starting points and has 4 plot choices, then 5 possible endings. So how many different adventures are there? Basically, you're going to make a choice of 1 at each of these different things. So I'm going to multiply them together. 6 times 4 times 5. Multiply it all the way out. Gives you 120 adventures. Okay, hopefully that's starting to make sense. We're just multiplying our number of possibilities together. Let's go with example 4. A password has 4 letters followed by 1 digit. So letter, 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 digit. I'm not going to write them out all the way. L's and D's, letters and digits. We are using uppercase and lowercase letters, which means I have 2 sets of 26 or 52 total letters that I can use. I want to know how many are possible if letters and digits can be used more than once. So I'm going to keep them the same. So I have 52 for the first, 52 for the second, 52 for the third, 52 for the fourth, and 10 again for my digit. All right, then I'm going to multiply all those out. I'm just going to write down our number here. 0. So about 73,116,160. That's what I get by multiplying all of these together. Okay. Just a quick note here. This is why passwords work. Okay. Passwords in themselves are not actually that secure, which is why they do get hacked sometimes. But in the end, if you're making a unique password, there's no good way to check all of these options, especially in the fact that most websites don't tell you have to use a letter or number first. They don't tell you it has to be so many characters. All of that just opens up more possibilities, and it's harder and harder to check. All right, let's go to the back of this page here. Continuing with some of these same types of questions, I want to know how many ways can a student council select a president, vice president, secretary, and treasurer from a group of 6 people? So this one's changing slightly because I'm picking from the same group every time. Everything I've been working for so far has had at least 2 groups that I'm working with. So I got to be careful with how I do this. So I'm going to work through this kind of one role at a time. So let's say we pick the president first. Well, if I have 6 people total, I have 6 choices for that president. Okay, now we are going to make the assumption that no one can hold 2 of these positions. I think that's a fair assumption to make. If we go to vice president, if I've already chosen a president, that takes 1 person out, so there are now 5 people left. I can do the same thing for secretary. I've now chosen president and vice president, so 2 people are gone. That leaves 4 left that I could pick from. And finally, treasurer, I've chosen 3 positions, so that leaves 3 people left, and I can multiply those all together. Okay, when we go ahead and do that then, I multiply 6 times 5 times 4 times 3. We get 360 ways that we can choose those 4 different positions. Okay. Slightly different example, we're going to have a stylist is arranging 5 of 8 vases from left to right in a store display. Okay, so we're just going from left to right. That means we have an order that we're going in. That's kind of important so that we know we are picking one and then it can't be chosen again. So I have 8 vases to pick from, but I'm going to choose 5 of them to put in order. So the first one, I have 8 choices for. The second one, I only have 7 because I've already used one. Third is going to be 6. Fourth is going to be 5. Fifth is going to be 4, and I know I stop here because it said I was picking 5 vases. This is first, second, third, fourth, fifth vase. Those are the number of options that I have. Multiply them all the way out, and I get an answer here of 6,720. So these numbers are going to be relatively big. That's part of the problem with probability is they get very big very fast. Number 7, last one kind of these types before we get into the true probability. We have the awards are given out at a costume party for most creative, silliest, and best costume. There's 8 contestants. No one can get more than 1 award. So we have 3 things that we're basically giving out: most creative, silliest, and best. We'll say that we just go in that order. So most creative, I would have the choice of any of the 8 people. So I'd start with 8. For silliest, I would already have chosen 1, so there's only 7 left. And best would only be 6. Multiply those out. 8 times 7 times 6 gives us 336 possible ways to do that. Okay, so those are all based on the fundamental accounting principle. Hopefully you can kind of work your way through those. Kind of just talking about how we count things and come up with all those different ways. That's going to become important when we start to talk about probability. Okay, I'm sure you've heard that term probability before, but let's give a definition here for it as well. So probability is the measure of how likely an event is to occur. So in other words, how often is it going to happen out of the total possibilities? Okay, or what are the chances that it happens? Okay, is another way to say it. Okay, with probability, we talk about outcomes a lot. An outcome is going to be a possible result. So it is each possible result. Okay, the sample space is what we refer to as the set of all. All is important there. I should capitalize it. You can circle it, highlight it, do what you want to do, but all is important. Okay, this is all possible outcomes. Okay, so in school we would talk about a lot of different sample spaces and things that can happen, but let's just kind of talk through a couple. Actually, let's do event first and then we'll get to it. So an event is going to be a specified outcome. Or it could be a set of outcomes as well. It might be more than one. Set of outcomes. Okay, so either one outcome or a group of outcomes. So let's talk about sample space. Let's say I am picking a card from a deck of cards. Okay, this is going to be a common one that we talk about as well. With playing cards, there's 52 cards in a deck. So all 52 of those cards are a part of the sample space. Okay. If I'm flipping a coin, my sample space is simply heads or tails. Those are my possible outcomes. If I'm rolling a die, or what we refer to as a number cube, I have 6 options. I have each of the sides, and that's actually my first example here for number 8. Rolling a 6-sided number cube, which is your normal just dice you play Yahtzee with. Okay, just one of them. Your possible options is I could roll a 1, I could roll a 2, I could roll a 3, a 4, a 5, or a 6. That is all of the possibilities. There is nothing other than those 6 things that could happen. Okay, let's talk about the next one. This one gets a little more complicated because now I'm doing 2 things. I'm flipping a penny and a quarter. So let's think about what could happen. Well, they could both be heads. We'll call that HH. They could also both be tails. I could have one be heads and one be tails. So let's say the penny is first. So the penny is heads, the tails is the quarter. Or that could switch. I could have tails on the penny and heads on the quarter. And I think that's probably all of my possibilities. Either they're both heads, both tails, or one of each, but I could switch which one is it, which is why I get the 2 options there of heads, tails, and tails, heads. Okay, so these are sample spaces. The really important thing is that we list out all of the options. If you don't list them all, you haven't really listed the sample space. Okay, let's talk about probabilities just a little bit more here. Probabilities can be written as a fraction or a decimal or as a percent. Okay, so you get the choice. You can either write it as a fraction, a decimal, or a percent. No matter what option you choose, whether it's a decimal, a fraction, or a percent, your probabilities can never be more than 1 or less than 0. Probabilities always have to fall between this range. Okay, and that should start to make sense as we start to talk about what probabilities are. Probabilities are that chance that something happens. If I have a 0% chance of something happening, that means it's impossible. It's never going to happen. It's physically impossible to happen. So an example of this might be I'm pulling out cards from a deck, and I ask you, what is the probability that I pull a 15? Well, a 15 is not a card in a deck, so it's not going to happen. It has a probability of 0. But we also have events that are the complete opposite of that are always going to happen. Okay? For example, let's say I'm flipping a coin. What's the probability that it's heads or tails? Well, those are the only 2 options, so one of those 2 things is going to happen. That's 100% certain. Okay, so we kind of have this range of things. Right in the middle at 50% is it's as likely as not, meaning it could happen or it could not happen. Okay, and we get this spectrum of things. Sometimes good probabilities are great, sometimes they're not. Sometimes we want lower probabilities. And so that range isn't necessarily a good versus bad. It's just the range that we have of it's impossible versus it's certain. Okay? And so that's really important to keep in mind as we go through these problems, that if you get answers that are outside of that range, they're not right. You have to go back and fix them. They have to be between 0 and 1. Okay? So let's start to talk about how we might find these probabilities. Okay? So we're talking about these outcomes. Okay, and so when outcomes have the same chance of being, of happening, we call these equally likely events. Okay, equally likely events. That's like flipping a fair coin. It's 50-50 between the 2 sides. Or rolling a fair dice. That it's 1/6 for each of the sides. That's not always the case. Sometimes we have skewed things, they're unfair things that make those probabilities change or those events change. We also have what we call favorable events. Favorable outcomes are the outcomes that we want in order for a specific event to happen. So if my event is that I roll a number that's bigger than 4, my favorable outcomes are 5 and 6 because those are both bigger than 4. So my favorable outcomes are kind of the outcomes that make up the event. You can think of it that way. For theoretical probability, this is the one that we do most often, but sometimes we do go to experimental. That's the other type that we'll talk about as well. So for theoretical, this is going to be the ratio of the number of favorable events to the total number of outcomes. And ratio just means fraction. So the favorable events go on top, the total number of outcomes go on the bottom. So essentially we get this here. Okay, now, just a quick notation thing. This P of event, okay? A lot of times you're going to see P and then something in parentheses, okay? That something that's in parentheses is the event that I want to happen. So if I say something like P1, okay, and I'm rolling a die, I'm saying what's the probability of rolling a 1. Okay, so just some notation there. You'll see some of that on your homework. Okay, the way I calculate that is the number of events or the number of outcomes where that can happen divided by the total number of outcomes in the sample space. So let's try one of these. Example number 9 here. I have each letter of the word probable is written on a separate card. The cards are placed face down and mixed up. What is the probability that a randomly selected card contains a consonant? And now a consonant are letters that are not vowels, so not A, E, I, O, or U. We're going to consider Y to be, but we don't have Y anyway. So I have a total of 1, 2, 3, 4, 5, 6, 7, 8 letters. So I know that my probability here is going to have to be out of 8 because I have 8 total. If I look at those, 3 of them are vowels. Okay, I got the O, the A, and the E. And then the other 5 are consonants. So I want to know how many different ways can I choose a consonant. Well, that's my 5 consonants that I have. So my favorable outcomes, there are 5 of them. So my answer is 5 over 8. Okay, now if you want to, you can take that to the decimal, which is 0.625, or the percent, which is 62.5%. Any of those answers are okay. You do not have to have all of them, although you can. Okay, I want to make that clear. For notes, I'm going to give you all 3 options for pretty much all of them, but you only need to have one on your homework. Okay, I'm going to go ahead and just pause for a minute and start a new video just so that it's a little bit broken up so you can come back and find things a little bit easier.